Good morning, everyone. Today, we're going to talk about gRPC and how to get started with it in Swift. If the clicker works. What if designing service APIs felt as natural as writing Swift functions? This might sound like an odd question, but I think there's often a great disconnect between designing APIs and how we implement them. When you're writing your business logic, it feels natural. You already know how to craft interfaces with great APIs for your libraries and apps. But when you start thinking about service APIs, you usually start thinking in terms of HTTP verbs and endpoints. For example, you might think of an order endpoint that you post a request to. But when you cancel the order, do you delete the order resource? Or do you patch it with a new state? We're moving our clear intentional business logic to the semantics of HTTP. And I think there's an impedance mismatch here. We think about our ideas and business logic in terms of operations, which we want to expose via a service. But providing a mapping from operations to paths and HTTP methods can be difficult. There are lots of options to choose from. What endpoint do we use for each resource? Which HTTP methods should we use? What goes in the path? What goes in the query string or the body? This conversion isn't always obvious. It adds friction to creating your service API. But what if you could eliminate or minimize the translation step and bring your ideas closer to your API? You can do that with gRPC, which is a great alternative to REST and OpenAPI. Let me explain why. First of all, it's spec-driven. Your service API is defined separately from the implementation. But in gRPC, your service is defined as a collection of functions. This makes it easier and faster for you to define your service without worrying about the semantics of HTTP. gRPC has a great interop story because it's spec-driven. The spec is the source of truth for your API, so getting started is just a matter of generating code in the language of your choice. And gRPC has support for the most popular programming languages. Code generation is great. It saves you time, it reduces errors that creep in boilerplate code, and it provides consistent interfaces. If there's one point to take away from this talk, it's that you should be using spec-driven service development, be it with gRPC, OpenAPI, or something else. It also has great performance. gRPC uses Protobuf as its data format, which is lightweight and compact compared to JSON, while providing strong type safety guarantees. During the rest of this talk, we'll go over the fundamentals of gRPC and Protobuf before defining and implementing a service using gRPC Swift. Finally, we'll look at some more advanced features so that you're ready to take your application to the next level. Let's dive into the fundamentals of gRPC. gRPC is a framework for making high-performance remote procedure calls, or RPCs. OK, what exactly is an RPC? In simple terms, it's a way of executing a function on a different machine. You could think of an RPC as a conversation. They start with a greeting, some things are said, and then the conversation concludes. In gRPC, the client greets the server with some metadata, which includes the name of the RPC it's calling. The server responds with some metadata, indicating that it's happy to talk. The client and server can then send messages back and forth. The conversation ends with a status code, indicating the final outcome of the call. Most conversations are short, with the client and server each sending one message. But gRPC has first-class support for streaming, so conversations can be longer and more one-sided than this. And there are 4 communication patterns: unary, server streaming, client streaming, and bidirectional streaming. In a unary RPC, the client sends one message, and the server responds with one message. Just like our example where the client sent a coffee order, and the server responded with the order ID. In a server streaming RPC, the client sends one message, and the server responds with a stream of messages. These RPCs feel live. like getting real-time updates on the status of our coffee order. In a client streaming RPC, the client sends many messages to the server, which responds with just one. This is great when input spans a period of time. Imagine placing a coffee order by streaming audio chunks to the server, which would work out what you asked for and then replies with your order details. In bidirectional streaming, the client and server can send each other messages at any time and with any number of messages. Think real-time collaboration, like a two-way chat with customer services for when your audio-based coffee order didn't go exactly to plan. At the end of each RPC is a status made up of a code and a message. This is how the client knows the final outcome of the call. Most RPCs end with the OK status code. Some won't run to completion and will either be canceled by the client or won't complete quickly enough. Some errors are typically associated with the client. Perhaps the request was invalid, or the client didn't have permission to do what it wanted. The rest are typically seen as server errors, where the client couldn't have done anything different in order to avoid the error. gRPC isn't tied to a single message format, but in practice, the overwhelming majority of services use Protobuf. So let's talk about that. Protocol buffers, or Protobuf, play two key roles in gRPC. The first role is as the interface definition language, or IDL, you use to define your service API and messages. The second is as the efficient format used to send data over the wire. Imagine a simple model for a coffee bean that our service could use. The bean might have a name and an origin, which are strings, an altitude above sea level at which it was grown, perhaps a roast level, and an enum, representing as an enum, and the date at which it was roasted. It might look like this as a codable Swift struct. The equivalent Protobuf message would look like this. It all looks very similar. We've got strings, an integer, an enum, and a timestamp. When serializing messages of each, the Protobuf message was 3 times smaller than the JSON. The serialization was 10 times faster, and the deserialization was 20 times faster. While this is a toy example, I looked at messages from a few public APIs and found similar results. JSON payloads were typically 2 to 5 times the size of the equivalent Protobuf message, and both serialization and deserialization were an order of magnitude faster for Protobuf. These are significant differences which can have a real impact on the performance of your service. OK, how do we actually define a service and messages using Protobuf? Here's an example for a barista service that I've been working on. Let's break it down. The top of each protofile contains a few key bits of information. The first is the version being used. In this case, we're using the latest, which is edition 2024. The next line contains the package identifier, barista.v1. This is a namespace for the types defined within the file. You aren't required to specify a package, but you should. It will greatly reduce the risk of type collisions in the future. It's also a good practice to include an API version in the identifier as well. Following that is an import statement, allowing us to reuse a message defined elsewhere. This is great for code reuse. It also means you can separate out definitions across multiple files, making it easier to manage. Finally, we set the Swift prefix option, which overrides the prefix used for generated Swift types. Messages are the data structures in Protobuf and are made up of fields. The order request has 2: the type of coffee being ordered and the number of espresso shots to use. Each field is made up of a type, a name, and a unique field number. Field numbers are really important. It's how Protobuf identifies each field in the binary format. This means they must be unique and they shouldn't be changed. In our order response, the estimated prep time is a duration. That's the message we imported earlier. This is one of a so-called well-known types, commonly used types which are included in Protobuf runtimes so that you don't need to reinvent them. But Protobuf has a range of other built-in types too. It supports integers of various widths and with both variable and fixed length encoding, which gives you the flexibility to optimize the size of your messages. And these all map naturally to Swift's integer types. Other types map exactly as you'd expect. And there are enums, which are really named constants in Protobuf, which map directly to Swift enums. And Protobuf's one-of type, which maps to a Swift enum with associated values. Finally, there are containers. Repeated gives you an array, and map gives you a dictionary. One difference between Swift and Protobuf worth mentioning is optionality. Fields aren't required to be explicitly set, and there's no nil value per se. Instead, generated code for each field will have a so-called hasr property, allowing you to check whether a value was set explicitly. If no value was set, then reading from it will result in a default value: 0 for numbers, false for booleans, and empty for strings and collections. For scalar fields, you can also specify a different default value to be used. In this instance, we'll do the only sane thing and use 2 shots of espresso as our default. Setting defaults like this allows you to reduce errors. A client would have to go out of their way to ask for 0 shots. It also means messages are smaller. If the field isn't set, then no data needs to be sent for it over the wire. Let's take a closer look at the service definition. It's just a collection of functions, your RPCs. Each RPC has a name, an input type, and an output type. If you want to stream messages, just add the stream keyword to the output, or the input, or both. Note also that the code comments in your proto file are used to document your generated code. So documenting your service and messages with any expectations is strongly encouraged. We've talked about gRPC and Protobuf, and we've defined our service. So I think it's time to talk about Swift. gRPC Swift was started by the open source community back in 2016. The first major version was tightly coupled with Swift Neo in order to provide asynchronous APIs. Earlier this year, we released a new major version of the library, which embraces Swift concurrency. We split the library into 3 layers: generated, runtime, and transport. The generated layer provides your type-safe APIs. For most, this really means Protobuf, but gRPC isn't tied to Protobuf. You could use other data formats here, like flat buffers. The generated layer calls through to a runtime layer, which orchestrates the RPC. For clients, it does things like handling timeouts and retries. For the server, it deals with routing. But importantly, it also maps your RPC onto a stream, which is provided by the transport layer. The transport layer provides the communication between your client and server. Again, gRPC isn't tied to a single mechanism here, but in practice, HTTP2 is the most widely used. Another widely used transport is an in-process one, which is often used for testing, as it avoids the network altogether. To support this layering, the project is now split across 4 repositories in the gRPC GitHub org. gRPC Swift 2 provides the core abstractions and runtime components, effectively the runtime layer and the in-process transport. Another adds support for Protobuf and provides tooling for code generation. The Neo transport repository provides a high-performance HTTP2 transport built on top of Swift Neo. Finally, gRPC Swift Extras provides add-ons, like implementations of standard gRPC services, in addition to integrations with other Swift packages, like Swift Service Lifecycle. Let's start creating our barista service. We'll start with an empty Swift package and add a few dependencies. The first is gRPC Swift 2 for the common runtime components. Next, we need 2 Protobuf dependencies, one to layer Protobuf support on top of gRPC, and another to work directly with Protobuf messages. We'll need the Neo transport as well, so that our client and server can talk to each other over HTTP2. Next, we need to generate some code. The tool to generate code from protofiles is called the Protocol Buffer Compiler, or ProtoC. ProtoC works by parsing protofiles and feeding them into plugins, which in turn produce source files. We need 2 plugins here, one for our messages and another for our service code. We have 3 options for generating our code in Swift. The first is invoking ProtoC directly. This is the most flexible approach, but can be fiddly to get right, as you need to build the 2 ProtoC plugins and ensure they're wired up correctly. The second is using the SwiftPM command plugin provided by gRPC Swift. This takes care of building the two plugins and exposes their options as an easy-to-use command line tool. For both of these approaches, you'll need to add the generated code into your project and version control system. The final approach is using the SwiftPM build plugin. This works in a similar way to the command plugin, but is invoked as part of the build process and configured by a JSON file. This means your code is always up to date and that you aren't required to check it in. We'll use the command plugin. At the moment, our package structure looks a little like this, with the service we defined earlier in an API directory. The structure mirrors the package name in our proto file, and this is a strongly recommended convention to follow. It will make your life much easier. When you invoke the command plugin via the Swift package command, it will generate code into the source directory for all proto files found in the API directory. It generates two files for us, a gRPC.swift file containing the service code and a pb.swift file containing the Protobuf message code. The generated code for gRPC includes a client to call the service with and a service protocol to implement. These are generated into a namespace made up of the service name and Protobuf package name. In our case, that's barista v1 _ barista service. So let's implement the service. To do this, you need to conform a type to the generated protocol. There are actually 3 service protocols giving you differing levels of flexibility over the implementation. But unless you have good reason to do otherwise, start with the simple service protocol, as it's the easiest to use and the hardest to misuse. You can see the signature of the function looks a lot like our RPC definition. It has the same name, it takes an order request as input, and it returns an order response. The only extra bit here is the context. Let's look at the implementation. First, we check if the order is valid. If it isn't valid, we throw an RPC error with an invalid argument code. The type is provided by gRPC Swift, and it maps directly to the status I mentioned earlier. After that, we create an order and return the order ID to the client. Returning the response from the function tells gRPC that the RPC completed successfully. So gRPC will return the OK status code to the client. gRPC is doing its best to get out of your way so that you can focus on writing your business logic. Now we need a server. This is all the code you need for a basic HTTP2 server. We'll pass it a transport and a list of services, and then we call serve. We're using the HTTP2 transport, listening for plain text traffic on localhost. This is great for demos and examples. But you're far more likely to configure a real server like this, listening on all network interfaces and configured with TLS. The transport is configured with a set of sensible defaults, which you can easily modify to better suit your needs, like controlling how connections are managed. Let's move on to the client. It looks pretty similar. We provide it with a transport, just as we did for the server, and this gives us a raw client, which knows how to talk to the server, but doesn't know anything about the barista service. So this is where the generated code comes in. We wrap the raw client in a stub for the barista service, which gives us the type-safe APIs defined in our proto file. After this, it's time to order a coffee. I'll go for a flat white with 3 shots. One of the advantages of defining our API in terms of RPCs is that the generated code is much more user-friendly. Our RPC is like a regular Swift function. We don't have to unwrap the response, figure out what the content type was, and so on. We just call the function with a request, and we get back a response. If the RPC fails, then an RPC error will be thrown. One difference between these examples is the use of the with gRPC client function. The scope of the closure denotes the lifecycle of the client, so when the closure returns, the client will begin shutting down, letting existing RPCs run to completion, but stopping new ones from being created. The function will only return once the client has completed shutting down. The equivalent server function has the same semantics. It begins shutting down when the closure returns, and the function returns once the server has finished shutting down. However, there's no obvious signal for the server to wait for. You'd need to define your own. Or you could use the integration with Swift Service Lifecycle and have your service group manage the lifetime and provide that shutdown signal for you. Unary RPCs are great, but gRPC really excels when it comes to streaming. One idea I had for my barista service was a bean recommendation RPC. This is a great use case for bidirectional streaming because it's conversational. The client can send their preferences, and the server can make some suggestions. The client can then refine their preferences, and so on until they're happy with the recommendation. After regenerating our code, we need to update the service as it no longer conforms to the protocol. This looks a little different to the Unary API. The request is an async sequence of messages, and there's no return type here. Instead, we have an object for writing response messages back to the client. To implement it, we use a type I wrote earlier. It provides recommendations for single origin coffee beans grown in particular coffee lots, refining its recommendations based on its input. You could call it a learning lot matcher. We iterate the stream of request messages and feed each of them into the matcher. It produces a set of recommendations, which we write back to the client. I'm absolutely certain we'll love the recommendations. When the client stops asking for recommendations, the loop exits and the function returns, ending the RPC with an OK status. So let's look at the client call. Again, the API takes advantage of structured concurrency, making it easier for you to reason about the lifetime of resources used by your RPC. It's a bidirectional streaming call, so there are two streams, a stream of request messages and a stream of response messages. So there's one closure for handling each. The first, for writing request messages, where we send preference updates to the server. Returning from the closure signals to the server that the client won't send any more messages. This is what triggers the for loop in the service to return. The other closure is for handling the stream of response messages. Returning from the closure signals that the RPC is no longer needed, so gRPC can clean up any remaining resources associated with it, like the underlying HTTP2 stream. OK, we've walked through creating a service from scratch, but there are a few more features you should know about before deploying your service. In the client example, the transport had a target parameter, which we passed a DNS target to. I glossed over the details, so I'll expand on them now. The argument we specified was the target for gRPC to resolve. gRPC will create a name resolver for that target and use it whenever it needs to establish a connection. When queried, the resolver will return a list of addresses for the client to use. For your real application, you're most likely to reach for the DNS name resolver. But there are other built-in resolvers, like for Unix domain sockets, and virtual sockets, and pre-resolved IP addresses. But this API is extensible. You can create your own resolvable targets and name resolvers to use with the client. This is effectively a service discovery mechanism. Your custom resolver can ask an external source which hosts to connect to. This gives you a great deal of flexibility. Resolvers can be pool-based, like the DNS resolver, where the client asks the resolver for a new address list. And they can also be push-based, where the resolver tells the client when that address list changes. The client dynamically adapts to these changes, opening and closing connections as and when necessary. And this helps support client-side load balancing. In traditional load balancing, each client will connect to a load balancer, which maintains connections to each backend. The load balancer will then direct requests to different backends. In client-side load balancing, each client maintains connections to multiple backends. It distributes load across them without the need for an extra network hop. And this can all be configured via ServerSide.config. ServerSide.config specifies how a client should behave when interacting with a gRPC server. It includes load balancing configuration and RPC-specific configuration. You can specify a service config directly via the API, or it can be provided by a name resolver. The rationale is that when you discover where the server is, you should also discover how to interact with it. Remember that the client dynamically reacts to the outputs from a name resolver. This means that it can also dynamically react to changes in RPC-specific configuration. This gives you great flexibility to change configuration for all of your clients without needing to restart them. Let's take a look at a few different RPC-specific configurations. So timeouts are really important. Sometimes things out of your control go wrong, and clients shouldn't be left waiting indefinitely. You can configure a blanket timeout for all of your RPCs in your service config, or tune them per RPC. Users can also override them with values at the call site. Timeouts are also propagated to the server, allowing it to enforce the timeout and make it available so it can be propagated to any upstream calls. I just said that sometimes things go wrong. Well, the client has built-in support for automatic retries. This is great for improving the reliability of your application. Your service config can specify which RPCs can be retried and the conditions they can be retried under. You can also configure how the client backs off between attempts. And it also responds to the server pushing back and telling the client when it should retry. There's also support for hedging, which you can think of as a preemptive retry. The client makes the same call concurrently on up to 5 streams, potentially staggering the start of each. It picks the stream which receives a response first and cancels the rest. This is great for reducing tail latencies, especially when you're using client-side load balancing, as each request may hit a different backend. As we've been talking about failures, we should also talk about errors. Earlier I mentioned that services can use the RPC error. However, as a service maintainer, you might not want to tightly couple some of your service components with gRPC. Imagine the barista service has a coffee grinder component, which throws an error when there are no coffee beans left. In isolation, it makes sense for it to use its own error type. The coffee grinder doesn't know anything about gRPC, and it doesn't need to. However, in our service, if there are no coffee beans, we should fail the RPC with a resource exhausted status. One option you have is to conform the error type to the RPC error convertible protocol. This provides a mapping to an RPC error, allowing you to throw your own error and have gRPC do the conversion for you. gRPC also has a richer error model for when you're using Protobuf as your data format. It allows the server to return additional details as Protobuf messages alongside the status for the client to consume. There are a set of standard messages covering common needs like bad requests, debug information, precondition failures, and so on. If these don't meet your needs, you can also use your own Protobuf message. This allows the client to get structured error details from the server. Here we're checking for a bad request and see there are 2 field violations. The number of shots we ordered must be between 1 and 4, and we didn't specify which coffee type we wanted. By separating out violations, the client has a clear picture of what they need to do in order to provide a valid request, rather than having to iteratively update fields and retry until the request is accepted. Creating errors like this can be time-consuming, but doing so will make it much easier for your clients to understand what went wrong and easier for you to debug issues reported by your users. OK, we've got one more feature to cover. gRPC, not being overtly HTTP-focused, is in many cases a strength. However, it does mean that you can't easily test or debug services with tools like curl. The problem is that you need your service definition and you need to generate a client, right? Not so. gRPC solves this problem with the reflection service, which is just a regular gRPC service which provides information about services. There are a number of tools built around the reflection service, like gRPC curl. It enables you to do things like list the available services, list available methods on each service, and even make requests. All of this without having to generate any code or have the proto files available. To use it, you just need to add the reflection service to your server. This is covered in more depth in an example in the gRPC.swift repository. It's about time to wrap up and reflect on what we've learned. gRPC has a contract-first design philosophy, where you define your service API in an IDL like Protobuf. Your API is defined as a collection of functions, meaning that you don't need to worry about the semantics of HTTP. This means you can generate your code in any of the supported languages, which makes it quick and easy to get started. You've also seen how gRPC has great support for streaming, which gives you lots of flexibility when designing your APIs. We've also been through how to create a service from scratch and seen how easy it is to get started with gRPC Swift. We've also seen some of the more advanced features available in gRPC Swift so that you're ready to take your application to the next level. To learn more, check out some of the available examples or tutorials linked here. Thank you all for your time. I hope you enjoy the rest of the conference.